Assalamualaikum. We will present the topic of ohmic heating for blanching and pre-treatment in food processing. So, my name is Putri Asminti Mazan, and these are my group members. We have Izati, Ainin, Daphne, and Zulaika.
Hello, my name is Daphne, and our group will discuss about ohmic heating for blanching and pre-treatment in food processing. Blanching is a conventional method that briefly heats fruits or vegetables in hot water, followed by rapid cooling. It helps reduce microorganisms and activate enzymes, improving food quality and shelf life. However, excessive blanching can cause nutrient loss and increase energy consumption, leading to higher processing costs. Ohmic heating provides a better alternative. It uses electrical heating to inactivate bacteria and enzymes while preserving the food's nutritional value, texture, and sensory quality. It also requires lower processing temperature, making it more energy efficient than conventional blanching. Overall, ohmic heating minimizes nutrient loss, maintains product quality, and saves energy, making it an efficient and sustainable technology for modern food processing.
So now I will explain the principle of ohmic heating. So what is ohmic heating? Ohmic heating is a good processing technology that uses alternating electric field across a product, causing its water and ionic component to function as electrical conductors. In ohmic heating, it directly converts the electrical energy into the thermal energy inside food. So there are two laws that involve in ohmic heating. The first law is Joule's law. In Joule's law, the formula is Q equal to I squared multiplied by R and then multiplied by T. Q represents the heat of the product in unit kJ, and then I represent current in unit ampere, and then R represent the electrical resistance in unit ohm, and then T is represent application time in unit second, and then the second law involved in ohmic heating is Ohm's law. The formula for Ohm's law is V equal to I multiplied by R. V represents voltage in unit V, I represent current in unit ampere, and then R represent electrical resistance in unit ohm. The mechanism of ohmic heating starts with fluid contain water and ion, and then it acts as a conductor in the ohmic heating, and then the alternating current causes ion to oscillate, and the resulting collision and then produce heat, and then heating occurs uniformly throughout the food.
Now, I will be explaining about the application of ohmic heating in food industry. First, we use blanching in food industry to stop enzyme called polyphenol oxidase (PPO) and peroxidase (POD) from causing browning, bad taste, and nutrient loss in fruits and vegetables. Normally, heat is applied from the outside of the food, which can overcook the surface before the inside is heated properly. But with ohmic heating, electricity passes through the whole food at once, so it heats evenly from inside out. This stops the enzyme without damaging the color, taste, or nutrients of the food. Second, we use ohmic heating as a pre-treatment before drying. Drying takes a lot of time and energy, but ohmic heating helps by breaking down the food cell wall first. This lets water escape faster and more easily during drying, which saves time and energy. This is very useful for large factories. For example, when ohmic heating was applied to grapes, the skin became more permeable, meaning water could escape faster and drying time was reduced significantly. So, overall, ohmic heating helps the food industry to work faster, use less energy, and produce better quality of food.
And this slide presents the advantage and limitation of ohmic heating in food processing. First advantage is ohmic heating provides rapid and uniform heating, where it will generate heat directly inside the food, allowing faster and more even heating. Another advantage is that it helps maintain the nutritional value of food because the heating time is shorter, heat-sensitive nutrients are better preserved, while microorganisms and enzymes are effectively inactivated. For the limitations, ohmic heating is less effective for food with fat granules because it has low electrical conductivity due to low water and salt content, which can lead to uneven heating and affect the food quality. Another one is that electrochemical reaction can cause electrode erosion and small particles will get into the food and will increase the maintenance since the electrodes need to be inspected and replaced more often.
Ohmic heating generates heat directly inside the food through electric current, saving up to 4.6 to 5.3 times more energy compared to conventional blanching, which relies heavily on hot water and steam. This direct heating mechanism reduces heat loss significantly, lowering both operating costs and environmental impact. Because the heating is rapid and uniform, the nutritional value and sensory quality of the food, such as taste, texture, and color, are better preserved compared to conventional methods, which means less raw material is lost due to quality degradation. On top of that, Ohmic heating reduces water consumption during processing, improve product yield, and extend the shelf life of the final product, all of which contribute to minimizing waste and supporting a more sustainable food supply chain. For best result or for the best practice, particle size is important to ensure heat is distributed evenly throughout the product. Inconsistent size can lead to uneven heating which affect quality and safety. Additionally, the Ohmic heating process must comply with HACCP, which ensure every critical point in the production process is properly monitored and controlled to prevent any potential hazard to consumers.
Now, let's talk about the challenges of Ohmic heating in the food industry. First, Ohmic heating does not work well for all food types. Foods high in fat like fatty meats and oily seeds have low electrical conductivity. This means electricity cannot flow through them properly, causing uneven eating and enzymes that are not fully deactivated. Second, the electrical conductivity of food changes as it heats up. When temperature rises, conductivity increases and draws more current. This makes it very hard to control the heating rate. In a large factory, this is a big problem because different batches may end up heated unevenly and some with active enzymes still remaining, others nutrients already destroyed. So, while Ohmic heating is promising, more research and better equipment are still needed for improvement in the food industry.
Despite the advantages that ohmic heating has shown in food blanching and pre-treatment, there are a number of ways to make it more effective. One approach is to increase the electrical conductivity of the food, since conductivity influences the efficiency of ohmic heating. Electrical conductivity of the food can be increased by pre-treating the food with a saline solution through marination or blanching before ohmic heating. For foods with naturally low conductivity, adding electrolytes such as salt while heating can increase its conductivity. Another way to enhance ohmic heating is by combining it with non-thermal preservation technologies such as high-pressure processing and pulse-electric field. Studies have shown that combining PEF with ohmic heating can reduce blanching time by up to 60%, while integrating HPP with ohmic heating can lower energy consumption by 6.3-fold, hence increasing the electrical conductivity of food, and integrating ohmic heating with HPP or PEF can further improve its efficiency, making food processing faster and more energy efficient.
In conclusion, the application of ohmic heating in blanching and pre-treatment has shown great potential in transforming how the food industry approaches processing. It not only meets the growing demand for more sustainable and efficient production methods, but also ensures that food products remain safe and high in quality throughout the process. This makes ohmic heating a valuable technology worth adopting on a wider scale in food processing operation.